In this video, we're going to talk about higher derivatives. So essentially, the idea of higher derivatives is, can you compute more than one derivative for a function? While each derivative is unique, you can continually differentiate a given function. So for example, f prime of x, if that is differentiable, i.e. we can find the derivative, we say that f prime of x exists, so the first derivative exists, and we say that it is once differentiable. But can we keep on going? Well, if that exists, then, and if the second derivative, f double prime of x, exists, we call that twice differentiable. Okay, and you can continue going. For example, you can get f triple prime, and that would be 3 times differentiable. You can do the fourth derivative of x, and from third, we kind of switch our language from saying triple prime to saying the fourth derivative, and we just denote it with a superscript of 4 in parentheses. We kind of drop the language of the fourth or triple prime, whatever, using prime notation, and just use that because it becomes too many tick marks. And then if the nth derivative exists, we say that it is differentiable n times, or it is just the nth derivative exists. Okay, and so if we go ahead and find f prime of f double prime of x, and here again we're assuming that we're in the domain, so we're assuming I should make the caveat that we also want x to be greater than 0 here, just so we're able to compute the second derivative. And so if I go through and find the first, this should be relatively quick for us, and I'm gonna be a little bit sloppy on my notation and just use f prime because f is only of one variable. So f prime is equal to, this is just a basic power rule, so this is 8x cubed and then minus, and now we have a product, so I have to do the product rule. So I do the first, and I'm going to put this in parentheses, first times the derivative of the second, okay, and that's just natural, or 1 over x times 1, but again, I don't need to write that. And then now plus 2 natural log of x times the derivative of this, and that's going to be 10x. Okay, and just let's see, that's a big parentheses. And I'm just going to simplify this one more step just so we don't have to worry about this later on. And so this will be minus, this will be 5x, and then a minus 10x natural log of x. Alright, so now the first derivative exists, and this is all continuous again on the domain of x greater than 0, so we can go ahead and differentiate it again and obtain the second derivative. So f double prime is just going to equal, well, do the power rule again for this one, so that'll be 24x squared. This one will just be 5 with a negative sign, and then I'll have a minus. Again, I have a product here, so I'll open a set of parentheses, and I do the derivative. Let's see, I'll do 10x times the derivative of natural log, which we said just was 1 over x, and then let's see, plus, then I'll do the second natural log of x times the derivative of 10x, which is just 10. Okay, and I can go ahead and simplify this if I wish. I'm going to skip that for right now and just leave it at that. It does simplify a little bit, the 5, and you'll get a minus 10 here, so you'll get a minus 15. But other than that, there isn't too many simplifications. Okay, so just know that to obtain the second derivative, you just repeat finding the derivative with or from the first derivative. All right, nothing earth-shattering there. A couple of things from physics. So in physics, the concepts of position, velocity, and acceleration are all tied very closely together, essentially by derivatives. So if s of t is the position at time t, then velocity is the first derivative, acceleration is the second derivative. Okay, simple enough. So if we look at an example here, so we have our position at time t on a straight road is given by this. So we might be a little intoxicated or something because it's just we're oscillating back and forth on a road. Why? I don't know. We want to determine the equations that model velocity and acceleration during the trip. Okay. Well, let's start there. So if this is position, then the velocity is again just going to be the first derivative. And so if I go through and find that, it's going to be cosine. Let's see, the derivative of cosine is sine, minus sine actually, sine of pi t. And here technically we have an inside function. We'll talk about the chain rule in the next section, but essentially it's just multiplying by the derivative of what's ever inside here. So multiply by pi. Alright, and then and I can rewrite that as minus pi, just kind of pulling the constant out front, minus pi sine of pi t. Alright. And then if I want to find the acceleration, well, this is the second derivative of time, or second derivative of position, sorry. So going through and doing that again, let's see, this is just a constant, the minus pi, so I'll leave that there. Looking at the derivative of sine, well, that's going to be cosine, and then pi t. And I have to multiply by the derivative of the inside function, kind of like what we've been doing with the logs, logs and exponentials. So I multiply by pi, and my acceleration is just minus pi squared now, cosine of pi t. Alright, so now it asks the follow-up questions. When is the velocity equal 0? Well, let's see. Essentially, we're saying when is sine 0? And this is going to occur, sine is 0 whenever we hit a multiple of pi, right? So at 0, pi, and 2 pi. And we have to restrict this. So this is essentially saying that velocity equals 0 when sine pi t, let's try that again, when sine of pi t is equal to 0. And we know that this has to be 0, pi, and 2 pi. So essentially this is saying when t is 0, 1, or 2. Okay? And then so if we wanted to describe this in terms of position, well, this is actually when we are, if we recall the graph of cosine, okay, so cosine, quickly just sketching it here. Cosine starts up at 1, goes down to 0, goes down to minus 1, and then increases back up. Okay, and then this is 0, this is pi, and then out here at its other maximum would be 2 pi. So these represent the maximal cosine values, the maximal distance. So the maximal distances we are on the road. Okay, so remember that we may ask for rates of change, and so velocity is the rate of change of position, acceleration is the rate of change of velocity. So keep that in mind too. Alright, so brief overview of higher derivatives, essentially nothing earth-shattering. Just repeat the differentiation process that we've been doing so far.